So LeChatelier's principle is, it's a principle actually governed by this Henry Louis LeChatelier. And you guys did cover him in your previous course, 152. And the principle is pretty easy in terms of visualizing what's going on. And I'll try and summarize the principle shortly, because experiment number 3, which is next week, is based on this concept. Okay, it's based on this concept. So we already talked about the reaction quotient in the first section of equilibrium. Reaction quotient is basically the concentrations of the chemical that you are studying under non-equilibrium conditions. Under non-equilibrium conditions. And if you do products over reactant and you get this value Q, okay, then the Q value in relation to K equilibrium will help you determine whether or not the reaction is still moving in the forward direction or the reaction is moving in the reverse direction. And that's the whole idea of LeChatelier's principle as well. What you have is you have to have a system at equilibrium. Then you change the conditions so that now it's not at equilibrium, and whatever that concentration is at that snapshot in time will give you Q. Now, if you compare that value Q, products over reactant, not at equilibrium, to the equilibrium constant, then you'll be able to figure out in which direction, more products, more reactant, the equilibrium is going to shift. Okay, so that's what we are looking at. That's basically what Q gives us, and we talked about that last time. So as a reminder, let's say we have this value. We have an equilibrium constant of 0.19. We have a condition in which the concentrations of nitrogen, hydrogen, and ammonia are that. What we want to do now is calculate Q, figure out how is Q related to K equilibrium. We see that Q is bigger than K equilibrium. Therefore, that Q value, Q is always chasing K equilibrium. That's what LeChatelier's principle is about. Okay, the reaction will eventually shift towards equilibrium. So Q has to get smaller. In order for that ratio, products over reactant, to get smaller, okay, the products has to get small, the reactant, sorry. Yeah, for the number to get smaller, then the products has to get lower, the reactant has to get bigger. That's what we mean by Q getting smaller based on the math. Based on the math, in order for this number to be 0.19, this number has to get smaller, this number needs to get bigger. Okay, when you have a small number on top, big number on the bottom, then that ratio gives you a smaller value. Physically, what does that mean? It means the reaction's going towards reactant. It's shifting towards the reactant. And you can see that in this mnemonic device as well. Q's 4.2, K equilibrium's 0.19. Q is chasing K equilibrium. It's moving from right to left. The reaction is going in the reverse direction. Okay, you can use this numbering scheme as a helpful way to visualize the direction of the reaction. Okay, so this, I know there's a lot of words in this, and that's death by PowerPoint, but I really just want you to focus on this right here. The top is just, if you're going through these lecture notes, it explains exactly what LeChatelier's principle is about. It tells you that if you apply stress, then the reaction is not going to be at equilibrium. The reaction will shift towards equilibrium again in such a way that more reactant or more products are going to form until you get back to equilibrium. So in summary, what LeChatelier's principle states is that any change in status quo means equilibrium, prompts an opposing reaction in responding to that system. Okay, in other words, you put more reactant, it's going to prompt a response to remove that reactant, to make that reactant smaller. The only way to do that is convert that reactant to product. Okay, we remove reactant. It's going to prompt a response so that it makes up for that removal of the reactant. The only way that's going to happen is by converting the product over to the reactant. So it's going to cause a shift until you get back to equilibrium. That's basically what LeChatelier's principle is about. And you want to remember that for experiment 3, okay? Because it's always going to be asking you, so what does this say about LeChatelier's principle? When you look at your observation in experiment 3, it's basically telling you what the principle is about. So another way of visualizing this, because I know a lot of you are visual learners, is to think about the teeter-totter principle. And I sort of introduced this back in 15.01. But if you need to visualize what's going on, think about a balance. Okay, we're saying that the rate of the forward and the rate of the reverse are equal. That's why the concentrations are not changing at equilibrium. Doesn't say, and I stress this again, it does not say that the two concentrations are equal. It only says that the exchange are equal. That's what it says, that the exchange are equal. So we're at equilibrium. Then there is a stress. In this particular case, more product is introduced to that system. The system is at equilibrium. We upset it by adding more product. That's the visual here. Of course, if you think about a teeter-totter, that causes an imbalance and makes the right side, the product side, more heavier. How do you get back to balance? You got to remove some of these and put it to the other side. You can't just throw it out into thin air. There's only 2 ways to go. It stays or it goes to the other side. And in this particular case, it's going to go to the other side until you reach a balance. We can say that the reaction shifts to the left. The reaction favors the reactant. We can say reaction shifts to the left. That's the shorthand notation that you'll see in my questions or quiz. You say RSL, reaction shifts to the left, or reaction shifts to the reactant, RSR. If it shifts to the right, then we say, that's not good. Don't use that, because if it shifts to the right, we say RSR, and no, we never use reaction shifts to the reactant, or we spell out reactant. Okay, or we favor the products. There's so many ways of saying that, but you just have to be clear in which direction the reaction is shifting. Let's take a look at this one right here. The stress on the reactant side, that's this. You're adding more reactant for a system at equilibrium. Okay, of course, it upsets the balance. The reaction has to go back to balance by converting that reactant over to products. So what you guys are going to say is that more products are formed if there's more reactant that is added. There's a confusion here. And let me try and clarify the confusion. If you add more reactant, you might say to yourself, oh, more reactant. That means that you will see more reactant. You will see more reactant because you add more reactant. No, don't do that, because what will happen is that initially when you add more reactant, okay, that goes into the solution, but the reaction is going to respond and it's going to cause that reactant to convert to product. So what you actually see is the effect based on the introduction of reactant. And so what you will see is the production of more product. If this is red and this is blue, and you introduce more red, more reactant, okay? When you do that, in the end, what you will see is more blue. I know it's a contradiction, but why do you see more blue? Because the reaction responds to that stress by producing more product, and the product is blue, okay? What you will see in next week is that you have a clear solution. You add more chemical and the product is orange. And what you will see is that the reaction all of a sudden turns to orange. Why? Because more product is being formed. And then if you add more of the product, you see that orange disappear and turn clear. That's an indication that the reaction is shifting towards the other chemical. You use your observation, you use what you see to give you an idea of which chemical is dominating in the equilibrium so that you can state which direction the reaction is shifting. Okay, we use our observation so that we can see which chemical dominates when the equilibrium shift has occurred, and then we can state based on which chemical dominates at equilibrium, which way the reaction shifted. Here's another, the relief. Sometimes we take away the chemical. Sometimes we take away the chemical. So take a look at this. What we do is we remove the reactant. Again, this is called a deficit. We've upset the equilibrium. So the reaction has to respond to that deficit. The reaction responds to that deficit by converting some of the product to reactant until you get back to equilibrium. So whenever there's a deficit, it has to be made up. Whenever you put a stress or add, it has to be removed. That's the key idea on LeChatelier's principle. Okay. When there's a deficit, it has to be made up. When there's added, it has to be removed until you get back to equilibrium. So that's the thing. And then you can also play that game on the product side. Okay, you can play that game on the product side. And so if you need to visualize what's going on, you can always look at the teeter-totter or think about the math or think about the physical process. So many ways to look at this, but you want to get everything in sync. They all have to sing the same song, because if one tells you one and the other, the math tells you a different, then you've got a conflict there. It's not clear in your mind what's going on. Okay, and that's where mistakes can be made. So let's take a look at reactions that involves energy. Reactions that involves energy means that it's either exothermic or endothermic. Now the question is, well, that is not really a change in the concentration. Yes, you're right. It's not a change in the concentration when you change the temperature. What you do find out is that when you change the temperature, you change the equilibrium constant. And we'll talk about that shortly. But for now, I want to give you a visual view of what's going on. For an exothermic reaction, you can think of exothermic reaction in terms of energy being produced in a reaction. So we put energy on the product side. Exothermic, energy is produced. Delta H is negative. It's being released. It's being released by the system. Okay. So if you put energy on the product side, that means that if you add more heat, it's putting a stress on the product. The reaction should shift to the reactant side. If you remove heat, then it's like taking away from the product, and the reaction has to make up for that deficit. So in exothermic and endothermic reaction, if you want to visualize what's going on, you can think of energy for exothermic in terms of a product. And then you can see that in terms of increasing temperature, you're adding more energy to the product side. Yes, you're adding energy across the solution. When you have a test tube and it has reactant and product, and you increase the temperature, you certainly increase the temperature for both reactant and product. But the fact that it's an exothermic reaction means that the product is going to be more responsive. Okay, the products are going to be more responsive. You're adding energy in this visual aid to the product side. The reaction has to reverse itself. The reaction is going to produce more reactant. The reaction is going to produce more reactant for an exothermic reaction. When you cool it down, when you cool it down, it's like removing the energy. Okay, so in that particular case, what you will get is a teeter-totter that looks like this when you remove energy. So what happens? In order for the reaction to go back to equilibrium, more of the reactant has got to convert over to product until you get a balance. So for an exothermic reaction, adding heat will produce more reactant, reaction shifts to the left. Cooling it down is going to produce more product, the reaction shifts to the right. For endothermic reactions, we have that. Again, you basically have the same visual that I'm trying to introduce. Now for endothermic, energy is a reactant. And so when you increase the temperature, you're putting more stress on the reactant side. It's going to respond to that stress by converting that reactant to product. Okay, so that's a visual. But there is a math. That's the important thing. There is a math to this whole thing. And I'm going to explain that because it's good to wave your arms and say, this is what happens. And this visual aid certainly helps in terms of seeing what's going to happen. But there's always a fundamental reason. There's a science of why these things happen. And I'm going to show you the science of why these things happen. Before I do that, though, let's take a look at solubility. Again, this is important in terms of experiment number 3. This right here is the solubility of certain salts: sodium chloride, calcium chloride, lead nitrate, potassium chloride, potassium perchlorate, and cerium sulfate. And generally, you guys know this if you've been in the kitchen, if you've got salt or even sugar and you put it in water, it's going to dissolve to its solubility limit. You put more, it'll dissolve, and then all of a sudden it starts accumulating. And you wonder, okay, why isn't it dissolving? Because you've reached the solubility limit, okay? What you can do is trick the solution to dissolve more by heating it up. When you heat it up, the water molecules are moving faster. The solute is going to be bombarded by the water molecule. It's going to cause bonds to break, and then it's going to dissolve. So we can increase the solubility by raising the temperature. So here's the salt, here's the solid in equilibrium with its dissolved form. See, we can write everything in terms of a chemical reaction. Now, remember what I said? If you heat up sugar or sodium chloride, then the solution goes more in, the solute goes more into solution when you heat it up. So the question really is, well, if it goes more into solution, that means that the reaction is shifting towards the right. Okay, it's going from a solid to an aqueous, and that's upon heating. So the question I'm going to ask you is this reaction therefore exothermic or endothermic based on what we just talked about? If you guys can put something in the chat, okay. Exothermic or endothermic if it dissolves more when you put it in hot water? No respond. Well, I'm not going to tell you the answer. You guys figure it out. Oh, there's a response. Here's what, thank you for the response. Okay, I appreciate that. If it was exothermic, then energy would be a product. Okay, energy would be a product. In this particular case, if we apply more heat, then the reaction would shift to the left. You should start to see the chemical, the salt, the solid in solution precipitating out. You get more solid formation. But I just told you, as you heat it up in the kitchen, it dissolves more. So it's not really exothermic, it's actually endothermic. It's endothermic. As you apply more heat, more of that solid dissolves into solution. Okay, so we look at our result to give us an idea of the thermicity of the reaction. Those are questions I generally ask in your next quiz. So for these salts right here, these are all endothermic processed salt. When you add more heat, the solubility increases. That's what this thing is showing, except for this guy. When you apply more heat, the solubility decreases, which means that this salt is actually an exothermic solubility. Exothermic solubility. As you apply more heat, like right here, okay, as you apply more heat for this salt, it actually crashes out of solution. So remember this table. You guys will see this table a lot. Let me clear this up. Okay, you see this table a lot, especially for those of you in lab, experiment number 5. So most salts are positive heats of solution. That means it's endothermic. When the salt, remember delta H positive, endo, delta H negative, exo. When the salt solution is heated, more solute dissolve. Some salts have negative enthalpy, like cerium sulfate. When these salts are heated, the solute becomes less soluble. Okay, so keep that in mind. For a gas, like take your carbonation. Maybe you have a beverage. It might be a 7-Up. It might be ginger ale. It might be a beer. Okay, and what you have is carbon dioxide dissolved in that liquid. And then, of course, they have other chemicals in there. But in order to make it more crisp, okay, in order for it not to lose its carbonation, we actually cool it down, because when we put it up and put it on the room temperature, or even in elevated temperature, it goes flat. So the reaction that you guys are going to see is, let's say, a gas, okay, in the gas form, in equilibrium with the gas in the aqueous form. That might be carbon dioxide. Carbon dioxide in the gas form in equilibrium with carbon dioxide in the aqueous. So the aqueous is when it's in your soda, in your beer. The gas is when you start to see the fizzing and the bubbles. Okay. Okay. Let me go back to this. The reason why this most solid, when you dissolve it, is an endothermic process. And what we're doing right now is just looking at the results. Will you agree with me that if you take like a solid and you want it to dissolve more, you put it in warm water, you put it in warm condition. We're looking now at a solution. The solute and the solvent is water. So in order for something to dissolve more, you put it in, you heat up the solution. Okay, so we can write up a reaction. Let's say we have sodium chloride and it's a solid. You have the granular salt, and then we put it in water, aqueous. And we know that when we heat it up, this is the dominant form. You know that when you heat it up, that's the dominant form. If it was exothermic, then the energy would be in the product side. And when we heat it up, it would start to precipitate out. We would see more solid precipitating out of solutions. That's not what we see. That's not what we see. What we do see is the following. What we do see is the following. As we heat it up, more of it dissolves. That means that it's causing that reaction to move in the forward direction. The only way energy is going to cause that reaction to move in the forward direction when you raise the temperature is if it's an endothermic reaction. The reaction has to have energy on the reactant side. So I hope that's clear, okay? I hope that's clear. But thanks for asking, because sometimes that might be too fast. If you guys have questions, please ask for clarification. Now is the time to get clarification rather than have that misconception when carry on, and then you're using that misconception when I ask you a true-false question in your next quiz. So let's take a look at this. The solubility of a gas is just totally opposite to what we just talked about. Because take a look at this right here. We have a carbonated beverage, okay? if we want it not to lose its carbonation, we don't want it to go flat, we stick it in the fridge, right? We remove the energy. So we want it to be dissolved in the aqueous form. We remove the energy, we cool down the solution. If we take it out and warm it up, okay, what you will see is that the carbon dioxide, the gas in the solution, starts coming out. And you see that in the forms of bubble or fizzing. So that means that when you increase the temperature, you start to see the gas form. It's not going to be, this is the dissolved form. This is the bubbles. So that means that the solubility of a gas are generally exothermic process. Okay, that's what that means. Solubility of a gas is generally exothermic process. And that's very clear on this right here. Yeah, clear this. Okay, you can see that. Here, see a lot of bubbles here, few bubbles. This is actually warmer. We can say, let's say that this is 1 and this is 2, conditions 1, and this is condition 2. We can say that T1 is greater than T2. It's under warmer conditions. That's why you start to see that fizz. The gas is actually coming out of solution. The other way, of course, is by changing the pressure. And we'll talk about that later on. Okay, we'll talk about that later on. So let's take a look at this right here. The solubility of a gas, exothermic. If you are ever in a restaurant, when we get back to normal, I used to do this all the time when my daughter was younger. She's not young anymore. She's 25. She lives in New York. But I used to try and fascinate her with science, hoping that she would go into science. Didn't work. It went the opposite way. She went into journalism instead, okay? She works for NPR. But anyway, what I would do is I would take my beverage, ginger ale, 7-Up, and I would take a paper clip that I usually have because I'm usually grading, and I would take the paper clip and put it over the candle and heat it up, okay? Warm up the paper clip. It's got to be metal. It's got to be good heat conductor. Then I would take that paper clip and then I would put it in my beverage, and then all of a sudden what will happen is that it will fizz uncontrollably depending on the temperature. And that's one way of entertaining kids. And it would just fizz up. And I said, yeah, that's just science. And it's basically this idea that if you warm up a carbonated beverage, it causes the gas to lose its solubility and it comes out as fizz. Okay, so that's what you see right here. Try that next time you are in a restaurant and you have some carbonated beverage. Of course, don't drink it afterwards. Ask for a new glass. But that's basically what's going on here. Okay, it's basically what's going on here. This right here is a video that I've shown in the past. I don't really have time to do this. If you go to the PowerPoint show in Google's Doc, you'll see this. Basically what happened is that there's this lake sitting, it's basically sitting in like a volcano type structure. There's a crater in that volcano and it's very, very deep. And water can, of course, absorb carbon dioxide. There's a lot of carbon dioxide in oceans and in lakes. There's a solubility in the carbon dioxide. What apparently happened here was there was a earthquake and it shifted, just like if you have a soda and you shake it up, what happens is that the carbon dioxide that is in your soda now gets airborne and or it gets loose, and then there's something called the nucleation process. You learn that in organic chemistry. And then more carbon dioxide sort of aggregates towards that, and then it basically hits critical mass and then it starts fizzing. That's what happened in this Lake Nyos in Cameroon back in 1986. And people didn't know it, but there was a village beneath that lake, probably about maybe few hundred feet below, and this thing started to release carbon dioxide. Nobody ever noticed it, but because carbon dioxide is heavier than oxygen, it starts to go out of the lake and then slowly crawls down to the village below, another surrounding village. And of course, if the oxygen is displaced by carbon dioxide, you get asphyxiated. You can't breathe. And so overnight this happened, and the whole village got wiped out. Maybe there was a few survivors, but that's what happens here. And again, it goes to testify on the solubility of gas. You guys can take a look at that if you want. The video doesn't play on my iPad, so that's why I'm not showing that. Let me talk to you guys about the math in terms of why the reaction shifts when you change the temperature. First of all, do you accept that when I have a solution at equilibrium now, and I change the temperature, I'm not adding chemicals or removing chemicals? Remember, one of the principles of LeChatelier's principle is that if you add chemicals, it'll cause the reaction to shift because you're changing the concentration. You're changing the expression in the mass action expression. If you remove chemicals, you're changing the conditions in the mass action expression. Only chemicals, though, that can change concentrations. Only chemicals that are aqueous or gas. If you add a solid or a liquid, that doesn't change anything. The equilibrium is just going to stay the same. But that's for another discussion, okay, that we've already talked about. But let's take a look at a beaker or a test tube, and we start heating it up. We're not adding or removing. All we're doing is heating up that temperature or heating up that solution. And yet the reaction is shifting. So what is going on that causes that reaction to shift? I already told you, the only thing that you can do, what is affected is the equilibrium constant. So that means that the equilibrium constant is changing under different temperatures. Now, at the old temperature, okay, you have one equilibrium constant. At the new temperature, you have another equilibrium constant, but now you're at the new temperature. But the conditions are such that you have reactant and product at the concentration to equal the old equilibrium constant. That old equilibrium constant is not the true constant anymore. It's now Q, because you have a new conditions. So the old equilibrium constant, upon adding heat or removing heat is now the Q value. The Q is always chasing K equilibrium. The chemicals have to change so that now it equals the new equilibrium constants. That's why the reaction shift, because you shift the equilibrium constant. The chemical still thinks that we have to satisfy this old equilibrium constant, but now the temperature has changed. It's going to have to shift to that new equilibrium constant. The reaction has to increase or decrease its component to equal the new equilibrium constant. That's what's going on in terms of the mathematics. And I know there's a lot of words here, but that's essentially what's going on. At the old temperature, when you change it to the new temperature, that old temperature, that old K equilibrium now becomes Q. And Q is always chasing the new equilibrium, the new conditions, okay? So that's why we have that shift. And it's sort of explained here, but this is basically the summary right here. The old temperature now becomes Q, and now that Q is going to change the new equilibrium constants for. So for endothermic reaction, what happens to the equilibrium constant? For endothermic reaction, the equilibrium constant, new equilibrium constant is actually higher than the one at low temperature. When it's higher, okay, for an endothermic reaction, when it's higher, then when we increase the temperature, that means that the reaction is going to shift to the right. It's consistent as well of what we just talked about. Endothermic reaction, we heat the temperature, the reaction shifts to the right because energies are in the reactant side. It's also consistent with the fact that endothermic reaction, K equilibrium gets to be higher at the new temperature. Therefore, the lower temperature has a Q value that is going to go to, it's got to get bigger in order to satisfy that higher temperature condition. So that's what happens when we raise the temperature. What happens when we lower the temperature for an endothermic reaction? When we lower the temperature for an endothermic reaction, that new K equilibrium constant gets smaller. The OD equilibrium constant has a certain value. In order for that to get, that ratio to get smaller, the reaction has to shift to the left, okay? And you can do that same argument for exothermic process, You can do that same argument. So the key here, the take-home message here that I'm trying to illustrate to you is that changing the temperature doesn't immediately change the concentration. It does immediately change the equilibrium constant. Now the chemicals have to respond so that their ratio is going to equal that new equilibrium constant, and it's going to either shift to the left or to the right until that old equilibrium constant becomes the new equilibrium constant at the new temperature. That's basically what is going on when we change temperature. The concentrations will eventually change so that it satisfies the new equilibrium constant. That's why whenever I write a problem, okay, I usually quote a temperature with the equilibrium constant, because that equilibrium constant will change as soon as you change that temperature. So that's what we have right here. Now this is this pertains very much so to experiment number 3. In experiment number 3, for those of you at Miramar College taking a lab, you guys are going to do this reaction. You're going to have cobalt chloride in equilibrium with hexaquo cobalt 2. So one is going to be blue, the other one's going to be pink. And the question here is that, is this process, this reaction as written, an endothermic process or is it an exothermic process? Look at this drawing. In this drawing, this is warm, T1, and this is cool, T2. So we can say that T1 is greater than T2. Okay, see the ice? You have ice here. So I'm going to have a poll and you guys just pick one of these questions. There's a poll that I have. Let me just, okay. And you just select on your computer, what do you think this reaction is? Is it exothermic, endothermic, or cannot be determined? Let's take a look, okay? Always go through the process. Cold temperature, this is the chemical that dominates at cold temperature. Warm temperature, this is the chemical that dominates at warm temperature. So when you heat this reaction up, it shifts to the left. That's warm temperature. When you remove and cool it down, it shifts to the right. Okay, that means this reaction is an exothermic process. So for the 41% of you who said that this was an exothermic, you get the prize for the day. And how do I know it's exothermic? Because of the experimental results. That's what experiment 3 is about. When you cool it down, so you're removing energy. Let's put energy here, okay, so that you guys can see this. Let me clear it up first. Let's put energy here. When you cool it down, then it's like putting a deficit on the product side. The reaction has to respond by producing more products. And that's what you see. You start to see more of the pink chemical. Okay. If it's an exothermic reaction and you put in more energy, you heat it up, then the reaction shifts in the reverse direction, you see more blue, and that's exactly what we have here. This is a higher temperature. It turns blue at higher temperature and it turns pink at lower temperature. This is an exothermic process. Okay, it's an exothermic process. And that's the reasoning that you guys need to apply when you have these types of questions. Okay, you look at the results, you think about which chemical dominates because of the effect that happens. Okay, and then you conclude whether it's going to be an endo or an exothermic process. I hope that's clear, because that really is important. That's the gist of this particular section. Okay, so you guys can take a look at that, write that in your notes for experiment number 3. Okay, the last thing I want to talk to you guys about in this 5 minutes is pressure changes. For solids and liquids, doesn't happen, doesn't change the equilibrium. Why? Because when you apply pressure on a solid and liquid, they're already compact. You're not going to make the size smaller. So it has no effect on solids and liquid. There is no shift in the equilibrium. And that's true as well, because solids and liquids do not show up in the mass action expression, only aqueous and gas. And when we talk about pressure, okay, we're looking especially at the gas form, okay, and we're looking at Henry's law. We're basically taking the gas and making it smaller. That's what we are doing. I wish I could go on and talk to you guys about Henry's law. And if you dive, if you go scuba diving, this is very important, because if you come up and the gas is released when you are compressed underwater, then the nitrogen comes out of your blood and you get the bends. But I'm going to skip that. You guys can take a look at that. What I want you to see, however, is that there's a mathematics in terms of what's going on when you increase the pressure. And you can only increase the pressure by changing the volume. So pressure changes via volume change. This is important. Take a container, okay? We want the pressure to increase. So the way we make that pressure increase, according to Boyle's law, is we make the volume smaller. We basically squeeze the molecules to a tighter point, okay? So when we decrease the volume, the pressure increase. So according to the Boyle's law, there's an inverse relationship between volume and pressure. When the pressure goes up, the volume goes down. That's Boyle's law. Okay, but here's really what's going on in terms of equilibrium. Let's take a look at this. We have our reaction again. This is the Haber reaction, nitrogen, hydrogen, and ammonia. And let's say that we have these concentrations, and it's at equilibrium, 0.1207 molar hydrogen, 0.0402 molar nitrogen, and 0.00272 molar ammonia at 1 liter. That's the key, at 1 liter. Okay, so we have this right here. We have this right here. I'm going to clear this out. And that equilibrium constant is 0.105. Now, suppose we take that reaction vessel and we increase the pressure by making the volume half the value. We go from 1 liter to 0.5 liters. Look what happens. Okay, we're going to make the volume smaller by half. Look what happens to the concentration. The concentration now is going to double. Why? Because if you got a mole in 1 liter, you get a concentration. But if you have a mole in 0.5, that doubles the original concentration. It's now same number of moles in a smaller volume, the concentration doubles. Look what happens. This doubles, this doubles, this doubles. Okay. But You're not at equilibrium anymore. Remember, we haven't changed the temperature. All we did was change the volume, which caused the concentration to change. Now you have Q. Now you have Q because you've changed the concentration by changing the volume. This value right here is smaller than K equilibrium. The reaction has to respond to that. And you can think of that in terms of our teeter-totter analogy. Let's take a look at this right here. And this is the last thing I'll talk about until next week. Okay. Look at this balance equation. Look at this balance equation. We've got 1, 3, and 2. Count the number of moles based on the coefficient of the reactant. 3 plus 1 is 4. Here it's 2. So according to our balance equation, we have 4 moles of gas on the reactant, 2 moles of gas on the product. Which side is more sensitive to pressure? The one with more moles of gas. So I would put P on the reactant side, the side that has more moles of gas. And then I will ask you, using the teeter-totter concept, if I increase the pressure, which way should the reaction shift? And you would say, oh, pressure in this example with more moles of gas on the reactant side, 4 versus 2, well, you're putting more stress on the reactant side. Therefore, if I increase the pressure, the reaction should shift to the right. And that's exactly what the math tells us. We have a Q value that is 0.262. We have a K equilibrium value of 0.105. When we increase the pressure by making the volume smaller, the reaction has got to shift to the right. Both the teeter-totter idea and the math tells you the same story. Okay, so if you want a visual aid in terms of pressure change, look only for the moles of gas. Only gas, not aqueous. Only gas. Count the coefficient on the reactant. Count the coefficients on the product. Which side is sensitive to pressure? You put a P there. Then you can treat it as either a reactant, if the reactant side is sensitive to pressure, or a product, if the product side has more moles of gas. Now, if they're the same, pressure doesn't do anything. A pressure change is not going to shift it one way or the other. A lot of the things that we did here wasn't so much math, it's mostly conceptually based. And you got to have a good feel of what's going on, because you're going to see that there's a bunch of questions. Take a look at activity number 6 for those of you in lab. That whole activity is based on LeChatelier's principle and K equilibrium. Okay. LeChatelier's principle applies when we change concentrations, when we add heat or remove heat, thereby changing the temperature. Remember that when you change the temperature, you not only change the temperature for the reactant, but you also change it for the product, because you cannot isolate a reactant and a product when that conversion is happening in the same vessel. So you heat up or cool down both reactant and product, but you have to determine how the shift is going to occur based on whether that reaction is exothermic or endothermic. Okay, so that's the key there. And then in terms of the last stress that you can apply, you can change the pressure, but you can't change the pressure by adding another chemical that is not involved in the equilibrium. Okay, like if I have a reaction like this reaction right here, in which we have, pull this, in which we have nitrogen, hydrogen forming ammonia. Suppose that this particular reaction is in, say, 1 atmosphere total pressure. The 1 atmosphere total pressure means that the partial pressure of nitrogen plus the partial pressure of hydrogen plus the partial pressure of ammonia equals 1 atmosphere. So when you say the total pressure, that's the sum of all the chemicals in the reaction mixture. But suppose in that reaction vessel, you add argon. So you increase the pressure from 1 atmosphere to 2 atmosphere because you add argon. Well, the partial pressure of nitrogen, hydrogen, and ammonia hasn't changed. If the partial pressure of nitrogen, hydrogen, and ammonia hasn't changed, then the mass action expression hasn't changed, and the reaction is not going to shift one way or the other. Okay, so adding an inert gas does nothing to the equilibrium. Why? Because you're not affecting the concentration or the partial pressure of the chemical in the mass action expression. Only those chemicals in the mass action expression are going to be affected when you if you change the conditions. Okay, when you change those concentrations, then you will get a shift one way or the other based on Q. So adding argon or even a catalyst just means that you reach equilibrium faster, but you do not necessarily change the equilibrium constant. It's not going to shift one way or the other. You just reach equilibrium faster. So please keep that in mind. Okay, these are conceptual things that you need to understand in order to appreciate equilibrium. When you change the pressure, the only way you're going to shift that equilibrium is by changing pressure via the volume. You guys know from Boyle's law that the pressure increases when you decrease the volume. Okay, when you decrease the volume, you're in effect doubling the concentration, because remember, the concentration is moles over volume. So when you decrease the volume in half, okay, when you decrease the volume in half, you're doubling the concentration. When you decrease the volume, you basically increase the concentration. So that's how you affect the mass action expression. You don't affect it by putting in an inert gas. You affect it by changing the volume. Now look at this problem again. Nitrogen, hydrogen, producing ammonia. What happens if you change the pressure by adding in nitrogen? Okay, so let's say you have one total atmosphere for these gas at equilibrium, then you add more nitrogen pressure. Well, that's just like adding more nitrogen gas, which means that you're increasing the concentration of nitrogen. When you increase the concentration of nitrogen, because you've inserted more nitrogen, thereby increasing its pressure, then of course the equilibrium is going to shift to the right, because it's got to offset that increase. So these are the things that you need to understand in terms of LeChatelier's principle and how it plays out. This week, you guys in lab, we will see how LeChatelier's principle applies in 4 different reactions. You take 4 different reactions and you apply changes, and you see base whether the reaction is going to shift to more products or more reactant. And the evidence you have on that is making the observation. Of course, you're watching a movie, so you want to look at the characteristic change of the reaction mixture. Okay, so keep that in mind. That's what's going to be occurring in this particular case. Sure, I don't have any questions here. Okay, so let me move on to this right here. This is just a summary of what we talked about last time. Okay, and likewise here, let's take a look at this problem right here. Again, this is typical problem you will see in your next quiz. And what you need to do is you need to predict, first of all, whether the reaction is going to shift to the left, more reactant, or to the right, more product. So we can say left or right, or RSR, reaction shifts to the right, RSL, reaction shifts to the left. Okay, so this reaction, I'll explain it and you guys can try it, and then I'll post the answer probably in the next meeting. But this is what I want you guys to look at in this particular problem. Again, this is a typical problem you will see in if not in the next quiz, typically in a midterm or in a final. So you look at this reaction right here. Okay, you look at that reaction right there. And if you look at that reaction, you will see that that particular reaction, water plus carbon dioxide, goes to glucose and oxygen. You folks of science should recognize that that's photosynthesis. Okay, photosynthesis, where a plant will take in carbon dioxide and water and produce sugar, glucose, and oxygen. And you should know that in photosynthesis, whether that reaction is endothermic or exothermic, all you have to know is that you need the sun for plants to grow. Okay, so you should know that in this particular case, oops, I don't know why that ended. Sorry, my for some reason my iPad just closed. Let me open that again. Okay, here we go. So if you take a look at this particular problem, you'll see that one, it's photosynthesis, and then you have a bunch of stress right here. These are your stress. And this is the reaction at equilibrium. Pay attention to the phase. Why? Because only those chemicals in the mass action expression is going to affect the equilibrium. But you got to know the difference between molarity and moles. Moles is the individual chemicals, the individual molecules. Molarity is the individual particles in the volume it occupies. That's very important. So in the first case, we're removing carbon dioxide. Carbon dioxide is a reactant, and we're removing that. So we're removing that. You guys should recognize that, oh, we're having a deficit on the reactant side. The reaction has to respond to make up for that deficit. Of course, the reaction is going to move in that direction, move in the direction that will replenish the deficit. Now, that means that if the reaction is going to move towards the reactant side, more reactant in terms of moles is going to go up. So the moles are going to go up because the reaction's moving in that direction. And the reactant will go up and the product will go down because it's being consumed. So in terms of moles, which is right here, this first column here, okay, the direction of the reaction will tell you whether or not it goes up or down. When a reaction occurs, whether you have a solid, liquid, aqueous, or gas, the moles will go up. If the moles doesn't go up, the reaction doesn't go. Okay, again, I remind you that moles is different from molarity. Now, over here, we have concentration, molar concentration. What you have to do is look at those chemicals that are influenced by concentration change. That would be aqueous in the gas phase. Solid, however, is constant. That doesn't change. So keep that in mind when you do these problems. Okay, that's very important. I want to go to this right here. You add more catalysts. When you add more catalysts, then what's going to happen, of course, is that the reaction is just going to reach equilibrium faster. But because the catalyst is not in the mass action expression, then it's not going to affect the equilibrium one way or the other. And because eventually the reaction is just the same as if there was no catalyst, then the moles is not going to change at all either, because you're just reaching equilibrium faster. Okay, it's not shifting one way or the other. In other words, the Q value is not affected. The Q value is not affected. I want to include in here another example. Suppose we add glucose. Let's say that I add C6H12O6. Well, when we add glucose, what you should remember is that adding a solid is not going to affect the equilibrium. And so it's not going to shift the reaction. If it's not shifting the reaction, the mole is not going to change either. It's only when the reaction shifts, because of LeChatelier's principle, does the moles increase or decrease. But in this particular case, because glucose is a solid, it's not going to sway the reaction left or right. So everything sort of stays constant. And when you answer what happens to the moles of glucose, you need to remember, yeah, you add glucose, but you want to look at a snapshot after that change has occurred. After that change has occurred, does the amount of glucose go up or go down? It stays the same. So that doesn't change either. Okay. So whenever a stress is applied, you don't look at what happens to the concentration because you add or remove. You look at the concentration or the moles as a result of the equilibrium process. After a moment in time, the stress has been applied. You analyze whether it goes up, goes down, or stays the same. That's what you need to do in order to answer these types of questions. Finally, I want to address this last one right here. When you have 2 moles of water and carbon dioxide and oxygen are added at the same time. So we have a reaction vessel. Let's say we have a reaction vessel right here. Okay, and we have carbon dioxide, we have water, we have oxygen, and we have glucose. And of course, glucose is a solid, but we're adding in here carbon dioxide, water, and oxygen. And you might say it's pretty confusing just because there's more than one change occurring for this reaction. If there was only one chemical added, then it would be easy. Well, my suggestion here, and for those of you in lab as well, is analyze this via math. Analyze this using the mass action expression. Okay, start with, say, 1 molar of the carbon dioxide, hydrogen, water, and oxygen, and let that equal to, say, K equilibrium. And then see how that K equilibrium will change when you increase the concentration to 2 molar. Okay, the volume is not going to change. So when you go from, say, 1 moles to 2 moles, the concentration doubles, since the volume is not going to change when you have this. So if you analyze it that way, you should be able to answer which way the equilibrium shift and whether the moles of these chemicals will go up and down and whether the concentration goes up and down. Finally, in order to address the heat, think of heat as temperature or energy. Remember that if it's an endothermic reaction and energy is a reactant, whenever the reaction's moving towards the left, moving towards the reactant, then energy is released. Whenever the reaction's moving towards the product for this endothermic reaction, then energy is absorbed. So you can treat the heat or the energy as either a reactant or a product, depending on whether or not this reaction is endothermic or exothermic. You guys should know what photosynthesis is, so I'm not going to tell you this. So practice this, make sure you understand it. Those of you in lab, you have another example in your activity, okay? But understand how to analyze this table, because you will see it one way or another in either the next quiz or your midterm.